Red giants are evolved stars that have exhausted the hydrogen fuel in their cores and have entered a late stage of stellar evolution. They are characterized by their large size, cooler surface temperatures, and reddish appearance. Red giants represent a common stage in the life cycle of stars with low to intermediate mass, typically between zero point 0.3 and 8 solar masses. Here's everything known about red giants. Red giants form when stars deplete the hydrogen fuel in their cores, leading to dramatic changes in their internal structure and behavior. Once a star exhausts the hydrogen in its core, nuclear fusion of hydrogen into helium ceases at the core. This marks the end of the star's time on the main sequence as a stable hydrogen-burning star. The core begins to contract under gravity, while the outer layers expand. As the core contracts, the temperature around the core increases, igniting hydrogen fusion in a shell surrounding the core. This produces enough energy to cause the outer layers of the star to expand, forming a red giant. The expansion of the star's outer layers causes the surface to cool, giving the star its characteristic reddish color. The star's radius can grow to tens or even hundreds of times its original size. As the core continues to contract, it heats up until the temperature reaches about 100 million K, which is hot enough to initiate helium fusion. This process is called the helium flash, where helium nuclei fuse into carbon and oxygen in the core, marking a new phase of nuclear burning in the star. Red giants exhibit significant changes in their physical characteristics compared to their main sequence phase. Red giants are much larger than main sequence stars. Their radii can expand up to 100 to 1,000 times the radius of the Sun. For example, the star Betelgeuse, a well-known red giant, is about 764 times larger than the Sun. Despite their cooler surface temperatures, red giants are very luminous due to their large size. They can be hundreds to thousands of times more luminous than the Sun, depending on their mass and stage of evolution. Red giants have cooler surface temperatures compared to their earlier stages as main sequence stars. Typical surface temperatures of red giants range from 3,000 K to 5,000 K. This lower temperature gives them their characteristic reddish or orange appearance. The core of a red giant is composed primarily of helium, which is left over from the earlier stage of hydrogen fusion. As the red giant continues to evolve, helium fusion begins, producing heavier elements like carbon and oxygen. Red giants lose a significant amount of mass through stellar winds as they evolve. The outer layers are gradually blown away into space, enriching the surrounding interstellar medium with heavier elements, including carbon, nitrogen, and oxygen. Red giants pass through several key stages during their evolution. First ascent red giants, RGB. When a star initially becomes a red giant, it is on the red giant branch, RGB. At this stage, hydrogen fusion is occurring in a shell around an inert helium core, and the star is expanding rapidly. Stars on the RGB have low to moderate luminosities. When the helium flash occurs, the star becomes more stable. After the helium core ignites, the star moves to the horizontal branch, where it burns helium in its core and hydrogen in a shell around the core. Stars on the horizontal branch are more stable and have more predictable luminosities. Asymptotic giant branch, AGB. After the helium in the core is exhausted, the star moves to the asymptotic giant branch, AGB. This is the final giant stage for stars up to about 8 solar masses. During this phase, the star again expands and becomes more luminous as it burns helium in a shell around the core. The star becomes unstable, loses mass more rapidly, and sheds its outer layers to form a planetary nebula. The structure of a red giant differs from that of a main sequence star. The core is composed of helium and later carbon and oxygen, which is degenerate, meaning that the core's pressure is dominated by electron degeneracy rather than thermal pressure. Surrounding the core is a hydrogen-burning shell and, later in the AGB phase, a helium-burning shell. These shells produce the energy that drives the expansion of the outer layers. The outer envelope of a red giant is convective, meaning that energy is transported by the movement of gas rather than by radiation. This convective envelope is responsible for bringing processed material from the core to the surface, a process called dredge-up. Red giants lose significant amounts of mass through stellar winds, which become stronger as the star evolves. The winds from red giants can eject material at rates of 10 solar masses per year. This mass loss plays a crucial role in the star's evolution and the enrichment of the interstellar medium. For stars with masses less than about 8 solar masses, the red giant will eventually shed its outer layers entirely, forming a planetary nebula. The hot, exposed core becomes a white dwarf, while the ejected material forms a glowing shell of gas that we observe as a planetary nebula. For more massive stars, greater than about 8 solar masses, the red giant phase can lead to the formation of red supergiants, which are even larger and more luminous than typical red giants. Betelgeuse and Antares. These are famous examples of red supergiants. Betelgeuse, in particular, is a red supergiant in the constellation Orion, with a size about 1,000 times that of the Sun. Red supergiants eventually evolve into supernovae. As the core of the red supergiant undergoes additional fusion reactions, carbon, oxygen, and heavier elements, it will eventually collapse, leading to a Type II supernova explosion, leaving behind a neutron star or black hole. Red giants often exhibit variability in their brightness due to pulsations in their outer layers. Subclass of red giants, known as miravariables, are long-period variables that pulsate in brightness over periods ranging from several months to a year. These pulsations are caused by changes in the size and temperature of the star as it evolves. Semiregular variables. These stars exhibit less regular variations in brightness but are still known to vary significantly over time. Red giants are prominent features of Hertzsprung-Russell diagrams, which plot stars' luminosity versus temperature. On these diagrams, red giants form the red giant branch, RGB, a nearly vertical sequence representing stars that are expanding and cooling as they evolve off the main sequence. In globular clusters, the red giant branch is one of the most conspicuous features. These stars are older and more evolved than the younger, hotter stars on the main sequence. Red giants play an important role in the chemical enrichment of galaxies. During their evolution, red giants create heavier elements through fusion processes. Helium fusion produces carbon and oxygen, while the later fusion processes, in more massive red giants, produce elements like neon, magnesium, and silicon. As the star expands and contracts during its giant phases, material from deep within the star is mixed with the outer layers. This process, called dredge-up, brings carbon and other elements to the surface, altering the chemical composition of the star's atmosphere. Some red giants become carbon stars, which have more carbon in their atmosphere than oxygen. This occurs when dredge-up brings carbon from the star's interior to the surface. The fate of a red giant depends on its initial mass. Low-mass stars, less than 0.5 solar masses, these stars may never reach the red giant phase. They will burn hydrogen very slowly and eventually become white dwarfs after gradually losing their outer layers. Intermediate mass stars, 0.5 to 8 solar masses, these stars will go through the red giant phase, lose their outer layers, and end their lives as white dwarfs surrounded by planetary nebulae. High-mass stars, 8 solar masses, these stars will evolve into red supergiants and end their lives in supernova explosions, potentially leaving behind neutron stars or black holes. Several famous red giants and red supergiants are visible to the naked eye and have been extensively studied by astronomers. One of the best-known red supergiants, Betelgeuse, is located in the constellation Orion. It has been the subject of intense study, especially due to recent dimming episodes that hinted at potential supernova precursors. The brightest star in the constellation Taurus, Aldebaran, is a red giant and serves as a reference point for the evolution of similar stars. Antares, another red supergiant, located in the constellation Scorpius, is a bright and well-known red giant star. Red giants represent a fascinating and critical phase in stellar evolution. As they expand and lose mass, they contribute to the enrichment of the interstellar medium and play a key role in the life cycle of galaxies. Their ultimate fate, whether becoming white dwarfs or exploding as supernovae, depends on their initial mass, but their contributions to the universe's chemical makeup are profound.